There are a lot of ways to actually measure a change in capacitance that you might get from a capacitive sensor. We'll just talk about a couple of them. I'll also mention that there are a lot of just basic chips that you can buy that do a lot of this for you and provide a serial output. We're going to start with a really dirt simple way of actually measuring a capacitive sensor. In this case, you've already done this in your lab, so you might have some VN from a digital I/O pin on your Arduino. You have some resistance, and then you have, in this case, your capacitive sensor to ground. Now this node here you'd have going to an ADC pin on your Arduino because you'd want to be able to measure the voltage across this capacitor as it charges up and as it discharges. And you know by now that if I provide some kind of step input to this system from my digital I/O pin, I'm going to get a response that's going to look like this exponential right here. So this is defined by V out over V in is going to be 1 minus e to the minus t over tau, where tau in this case is my RC time constant for this circuit. And of course at tau, I'm going to be 63% of the way to my final value. So this would be 0.63 V in at time t equals tau. Now the game that we're going to play here is that if this capacitance changes, my tau is of course going to change because it's also based on that capacitance. So let's look at the case where that capacitance actually increases. Right, I'm going to have also an exponential, but it's going to have a slower rise time to that V in. So by the time I get to that tau value, this is my tau nu right here. And so this method of measuring the time constant, if I can measure the difference between these two, I can figure out what the new capacitance is as well. So in this case, I can back out my sensor value from my time constant that I might be measuring and my input resistance. And similarly, I can measure that change in capacitance by measuring a change in time constant divided by the resistance in my circuit. So as hopefully is also obvious, if I have some initial capacitance here and some new capacitance right here, this capacitance is larger. Assuming my resistance doesn't change, this capacitance is larger. So C2 in this case is greater than C1 because the tau is greater than the tau1. Tau2 is greater than tau1. Now if I'm trying to get a sense as to how well this works, if I have a change in capacitance on the order of 200 femtofarads, like I had in my last example, or 2 times 10 to the minus 13 farads, then my change in tau that I'd have to be able to measure would be equivalent to that delta C times some resistance. If I pick a pretty high resistance here, so R is a mega ohm, then in this case I'm looking at 2 times 10 to the minus 13 farads times 10 to the 6 ohms, and so I'm looking at 2 times 10 to the minus 7 seconds, or 0.2 microseconds. And this is a pretty big ask for the Arduino, for example. For the clocks on the Arduino, if you have a faster computer, this might be pretty reasonable. But this would give you kind of a lower limit. You're looking at something on the order of tens to 100 femtofarads will be your kind of capacitive resolution using this kind of method. Another very common topology to measure a capacitive sensor, in this case this might be this capacitor right here in this circuit. I have an op-amp, but really this is acting as a comparator, so you can see this is in both negative and positive feedback. So it's just going to a rail when this input is larger than this input. It's going to the positive rail. If this input, the inverting input, is larger than this input, it's going to the negative rail of the op-amp. So it's a comparator. This exists on a lot of microcontrollers, so people take advantage of this using a microcontroller that they already have. The basic idea of this circuit is I'm going to call this node right here in the positive feedback path Vref, and I'm going to call this node up here with the capacitive component, I'm going to call that Vramp. And if I know that this is going to a rail either time, so imagine it's going from 0 to 5 volts, these are two equivalent resistors, so this will be a square wave that is something less than 5 volts. In this case, it's around 2.5 volts. And the Vramp, right, as soon as I increase, right, as soon as this output goes high, then this will start charging up this capacitor right here. So it'll start going up like this until it reaches that point of Vref, and once that happens, this is now higher than the Vref, and so it will drop that output low pretty much immediately, right? This is a very unstable circuit. And so once that output drops low, that capacitor starts discharging. That was a very bad discharge, but the capacitor starts discharging like this, and then it'll kind of increase again, right? And I'll get this kind of bouncing back and forth. But what I'm really doing here is actually measuring the frequency of my output square wave. So my output will look like Vref, but just a lot bigger in amplitude. So let's look at the point if this capacitor increased a lot. So my discharge time would be a lot slower. So it's going down, 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 down. And finally at this point, does my Vref become larger again, and now I bump up. So you can see how my frequency of this has changed. And so if this takes a similarly long time to bounce all the way up again, right, this is going to stay like this. So I'm basically measuring this frequency here. I can use that with some of the timers on a microcontroller. I can use some of the timers on a microcontroller to measure that frequency, and so then I can back out what the current capacitance of my sensor is. So if I say the sensor was at some capacitance here, C1, and some capacitance here, C2, right, with this slower frequency, let's call this F2 and F1. F2 is smaller than F1, or similarly T2, the period of this is larger than the period of 1, is going to imply that my capacitance 2 is greater than capacitance 1. Because once again, this is based on a time constant. It's just a slightly different configuration than trying to measure tau explicitly. Let's look at one other approach that's very common in the world of MEMS, or microelectromechanical systems, and these are the sensors that are making the inertial sensors, for example, in your cell phone. They make MEMS strain gauges, all sorts of different things. But this is a very common configuration for capacitive sensors in the MEMS world. And this is looking top down at something that might be etched into silicon. This is kind of silicon that is Silicon Valley. And in this case, I have this mass, and it might be a very small mass, but this is attached to some ground link through some kind of spring, and damping might be from air in the package. But I have these comb fingers. So these are effectively, if I tried to kind of draw this in 3 dimensions, these are plates that are kind of sticking into the surface right here. And so if I look at the gap between these two plates as this mass is moving up and down, let's define plus x in this direction, then I'm going to get a gap between these two plates that's going to be G0 plus x, and a gap between these two plates that'll be G0 minus x. And the same thing will happen over here. I have G0 plus x, G0 minus x. And most commonly I have a whole lot of interdigitated fingers where I'm repeating this over and over. But once I have that, I can set up a circuit that's basically what we call a capacitive half bridge. So I have two capacitors in my circuit. I'm going to have a plus V in, and that's going to be an AC voltage right here, and the negative of that on the bottom. So I'm not using ground here, is kind of a key point. This is my V out. And then I have for this top capacitor, I have the capacitance that is increasing, and for the bottom one, I have the capacitance that's decreasing. Right? As my gap is increasing, my capacitance is going down. As my gap is getting smaller, my capacitance is going up. So let's call this one C1. This would be equivalent to C1. C2 right here, this one would be C2 in this particular configuration. All right, but if I'm trying to calculate what V out is for this particular circuit, I can just think of these as impedances. And now this is just an impedance divider, so I'm going to have the impedance of that bottom capacitance, ZC2, over ZC1 plus ZC2, right? So the impedance of the bottom over the impedance of the sum. And because I don't have ground here, I actually have to do my Vin minus whatever that negative supply is, in this case negative Vin. So these things are going to add, and then I add my ground or my negative supply to this as well, so minus Vin at the end here. Okay, so I know that the impedance of a capacitor is going to be 1 over j omega c, so I can start plugging those in here. I'm going to multiply everything through by j omega c1 c2, and so I'm going to equal c1 over c2 plus c1 times 2Vn minus Vn. And if I multiply this negative Vn times c1 plus c2, and I'm going to get, in the end, my V out is C1 minus C2 over C1 plus C2 times Vn. Alright, so my C1, just so I know how this thing is going, my C1 is going to be, let's just assume air here, so epsilon r is 1, epsilon naught A over, in this case, G naught minus X. And then my C2 is going to be epsilon naught, that same A, over G naught plus X. So I'm going to take these and plug them into this equation here. And when I plug those in, I get this, and I know it looks really messy now, but I promise it will look very pretty in the end. I'm going to multiply everything through by G naught minus X times G naught plus X. And so I'm going to get G naught plus X minus G naught minus X on that numerator. These E naught A's cancel, times G naught plus X plus G naught minus X, that whole thing times V in. So my G naughts on the top are going to cancel, my X's add, and then my G naughts add on the denominator, and my X's cancel. So this whole thing is just equal to X over G naught times Vn. Alright, that is V out. That whole complex thing just gave me this really nice clean relationship. So my V out is going to be a fraction of Vn based on what X is, the displacement is, relative to that initial gap. So a quick example of what this means, if I have a initial gap of 1 micron, say, and I have a Vn amplitude. So the amplitude, remember this is an AC signal because these are impedances. These aren't, DC doesn't work here. Say I have an amplitude of my Vn of 5 volts, then I can measure for a displacement that is let's say 10 nanometers, I'd get a V out amplitude that's equal to 10 to the minus 8 meters divided by 10 to the minus 6 meters times that 5 volts as well. So I'm getting 50 millivolts at my output, right? That's 50 millivolts magnitude of a sinusoidal signal, but 50 millivolts is something that's pretty straightforward to detect, right? That's not something that's really tiny, and I'm talking about measuring a displacement of 10 nanometers. So you can start to see some of the advantages of using capacitive sensing when you can make very small gaps.